This also isn't like a super advanced course either. It's kind of like Goldilocks. It's right in the middle there. So we'll be covering primarily three things. One is some of the considerations or what to pay attention to and what not to pay attention to when you're looking to build an enterprise blockchain app. So what are some of the characteristics, what are some of the trade-offs, and what are some of the things you can just ignore? We'll talk a little bit about data and how to manage data. This is one of the issues that I think is most plaguing to kind of building enterprise blockchain apps is blockchains or applications in particular involve a lot more things going on than kind of where the blockchain piece fits in. So how do we help coordinate all that? And we'll talk a little bit about maybe some considerations as to where things are going. So I'm with Fluree DB. We're a North Carolina company. We're up in Winston-Salem. And we're not going to really talk, it'll come up a couple times. We're not going to talk much about Fluree, but it's a database blockchain product that we have been working on for about 4 years. I'm the co-CEO. A little bit about me. I've been building enterprise software for about 25 years. The other co-CEO is Flip Filipowski, a good friend of mine. And we have built a good number of companies, had a couple public offerings so far to date, but as I guess we'd both be quick to say, in this industry, probably what you've done in the last 3 or so months is all that really matters. So I started my career doing development and been really just focused more on the business aspect. But when we started Fluree about 4 years ago, it really drew me back into the development side. It kind of got me to geek out a bit about blockchain. I love blockchain because the most interesting and I think challenging parts of computing, or at least that draw to me, are distributed computing and cryptography. And this is just an incredible mashup of the two. And you just have to deal with adversaries so much more in this space than you do in typical enterprise computing. So for me, that's very exciting. So to get things started, I figured we would talk about things we hear about blockchain, determine whether they're true or not, or determine if they even matter when we're building enterprise applications. So I put together a couple questions. Blockchains, does it matter that they're bad for the environment? Does anyone think they're bad for the environment? Some people, I hear this all the time. We shouldn't use blockchains, it's bad for the environment. I think in an enterprise blockchain implementation, this probably doesn't matter a whole lot because this primarily focuses around the proof of work algorithm, which Bitcoin, of course, uses. But most enterprise blockchain implementations, depending on what you're using, you're probably not damaging the environment any more than just running normal servers. So this probably doesn't matter. Blockchains are just big, slow databases. Everyone's heard about Bitcoin only doing 3 or 7 transactions per second. Is it true? Yeah, to a degree. Again, when we talk about blockchain, I don't know if anyone saw Amber's talk, but she did a good job of kind of introducing all these slices that people are thinking about blockchain problems around. And when you come from it from a certain angle, you have a perspective of exactly how blockchain's being used. And if you're thinking about Bitcoin, then in fact, both of these statements are true. But most of the technologies that we're using don't have these characteristics, so they're not things we particularly have to worry about. Are blockchains slower? Yeah, one of the things that is important to at least get your head around a little bit. When we're used to building enterprise applications, we're used to scaling out, our app tier layer, and we put a load balancer in front of it, and we of course want a request to go in and one server to process that business logic and give us a result. And the blockchains are almost the opposite of that. It's like putting a load balancer in front of it, except every server needs to process every single request and then talk to each other and make sure they come up with an agreement. So that does slow things down. But 3 transactions per second, we have technologies out there now claiming, in the case of the DAG technologies like Hashgraph, claiming 250,000 transactions per second. When we're building an enterprise app, sometimes these numbers don't even matter. In fact, very often they do. My last company was a HR software as a service company. And one of our largest customers, a Fortune 500 customer, we ran all their HR systems. They did about 1 transaction. This doesn't include queries. You know, that's different. This is just updating data. About 1 transaction per minute was the average. And that's a Fortune 500 company, all their HR systems. So it's a matter of perspective. Would I want to be like Datadog, who I saw their booth downstairs, trying to ingest billions of log files and store those in a blockchain? No, it's probably a pretty bad choice. So yeah, they're slow, but they're plenty fast for most of what we want to do in the enterprise. And a lot of this is going to depend on some of the consensus mechanisms we choose to focus on, which we'll talk a little bit. Blockchains must be resistant to Sybil attacks. I would, since we're in such a big room, I would ask people to explain some of this, but I'll just go through a bit of it myself to keep things moving. So a Sybil attack is where someone impersonates the identity of multiple people. And of course, when we think about public blockchains, this is really important because the key, obviously, with the public blockchain is that we're not constricting the participants in any way. And when we don't constrict the participants, we have no idea who the participants are. So we have to come up with consensus mechanisms that deal with this problem. And proof of work is a good one. Proof of stake is another one. But in an enterprise environment, in almost all cases where we're setting up a blockchain for a consortium or anything like that, we know who the participants are. So this becomes completely irrelevant to us in most of these implementations. We don't care, because we control the initial access or who's participating. Therefore, it's pretty easy to prevent Sybil attacks. This one, I think, is a little bit tougher. Does it need to be Byzantine fault tolerant? So the Byzantine generals problem, for those not familiar with it, it's sort of a mind theory problem that Byzantine generals, a bunch of them, surround a city. And they all need to decide together whether they're going to attack or retreat, because if half attack and half retreat, they would end up getting defeated. So the problem is what if there's a traitor in the mix? What if there's someone feeding bad information? So, say half say they're going to attack, half say they're going to retreat, and then the last deciding vote tells the first half attack and the second half retreat, and they would split up the network. So it's an important characteristic, especially in full public blockchains, that we need full Byzantine fault tolerance. But if we are building an enterprise app, and if that app has participants that don't have to fully trust each other, but they may partially trust each other enough to do some degree of business, is this critical to have? And in enterprise blockchains, what we're primarily using in a private blockchain, we're using the algorithm or some derivative of the algorithm, practical Byzantine fault tolerance. And so making this decision actually adds constraints on your network. In a sort of your typical PBFT setup, you need to support, for the number of failures you want to support, you need 3 times that plus 1 computers in the network. So to support a single failure, you would need 4 computers on the network. To support 2 failures, you need 7 computers on the network. Byzantine fault tolerance also involves additional technically 2 additional steps over something like Paxos or Raft, which is what a lot of our databases and Zookeeper, things like these that you've perhaps used are using. Those really just require majority. So, in a Raft protocol, you want to see typically 5 nodes on the network, and that allows 2 failures. So the same 2 failures in a PBFT network, you need 7 nodes to support 2 failures. So if you want to go Byzantine fault tolerance, you can. It's going to allow you to resist people feeding misinformation into the network. But importantly, as long as you have a good blockchain implementation, even if you're using something like Paxos or Raft that isn't Byzantine fault tolerant, it's not like someone's going to necessarily fake the data, but someone can much more easily take down the network. They can manipulate the information, but you still know who did what. You still have a record of that. So it's an important thing to think about whether or not you really need it. If you don't need it, you'll get more redundancy in your network for the same number of nodes, and you actually have a faster network because there's a couple less checks that need to be done. So blockchains don't have finality. Sometimes I hear people say they have finality, but for the most part they don't. Enterprise blockchains do. To a degree, something using Raft or Paxos or PBFT is going to have some degree of finality. And finality just means that you have some guarantee of when the transaction is done. And of course, when we think about building enterprise applications, this is always just a given for us. You know, if you create an invoice in your system or you put in an HR record, you get back the result from your app, and of course it's done. It can't be changed. But in the blockchain world, this isn't necessarily the case. You could have a confirmation of a transaction come back, and in the case that there was a fork or uncle in the network, then you could be in a situation where you thought you had something confirmed, but you found out 10 minutes, 20 minutes, 30 minutes later that it really didn't happen. So it's a difficult issue to contend with, especially when we have to somehow incorporate this into enterprise software. But it's something that can and does happen in public blockchains. So as long as we're doing a private or sort of permissioned blockchain across multiple organizations, then this probably isn't that big of a consideration. But if you are focused more on a public blockchain side, it likely is, or should be. So why are we doing this to begin with? And I think the best kind of tip of the iceberg term that everything in blockchain falls off of is around trust. And I think it's amazing how little, you know, we've come up with ways of dealing with it, but how little we can trust any of the information that's actually in our systems. When we are running any sort of internal system in our business, are we able to guarantee that a piece of data hasn't been tampered with? Whether it was tampered with by someone internally, or it was tampered with because you got hacked and maybe you didn't even know it, someone changed that information. The fact is we don't know. And in fact, we have built massive industries around the fact that we don't actually trust almost any of our information. And certainly other people don't trust us about it. And so this is, I think, what we have an opportunity to change using blockchain technology. I like, you know, we're not usually talking about cryptocurrencies when we're talking about enterprise blockchains, but Bitcoin to me is just this phenomenal piece of technology. It's this right combination of items that came together to exhibit these qualities that are pretty amazing. And when you think about what's happening with Bitcoin, it is the epitome of information security. We are so used to having our data, our databases, and we put firewalls around them, and we're trying to do everything possible to protect that information. But here's a database, essentially, it's a database that's not protected by anything. It's out in the public network. If you could hack it, if you could do something, you would become, you know, possibly one of the richest people in the world. I mean, there's plenty of incentive to hack this thing. Yet now it's been running for 10 years, and it's never been hacked. There's no security breaches around it. I mean, you've heard of some security breaches, but they're not in the Bitcoin protocol itself. They're in people who have set up services around the periphery of it. But this is pretty amazing information security. And why shouldn't all of our data have that sort of integrity? I think it should. I think eventually it will, and it can. But you think about just some of these industries that are at sit because we don't trust our information. So title industry, I think, is a great example. There's $15 billion spent annually on the title industry, and it's because we don't trust our land records. You know, we don't trust that someone might not claim that they own a piece of property. $15 billion industry in insurance that we just, you know, you're closing on a house, you just say, okay, this is something I have to do. But you don't think about why you have to do it. The reason you have to do it is because we don't trust our information. The audit industry, you know, a huge part of this is looking and verifying information and data. It's about a $210 billion industry. And of course, when we end up having problems in the supply chain or things happen, what it costs our businesses is massive. And I think the key, and it's probably hard to see, but the key is really down here at the bottom. If we can fully trust the data in the integrity of the information, then we can conduct business even if we don't fully trust the other parties. So I think it also opens up a lot of new opportunities for people to start working together. And these are some of the most exciting use cases that I have seen around this space. Exciting to me. I'll give two examples of a very similar one, type of use case, but two different industries. One is financial services. You know, they need to go through and do on every new account holder, know your customer and anti-money laundering law checks. And of course, they don't, you know, it's administrative work for them. It doesn't really add any value. So there are multiple startups now. I know most intimately the one that's approached us about using our product for it, but they want and have some endorsement for some of the big banks to start working together, sharing a blockchain network where they're actually sharing for this particular customer identity. I already did a know your customer check. And you can still do it if you don't really trust me, but here's, you know, proof that I went through that. And they can start sharing some of this administrative tasks. A similar use case that's come up for a startup recently is in the healthcare industry that I think is really exciting, and it's all around verifying doctors and verifying their resumes and their credentials. This is something that's very expensive to do. Obviously, it's pretty critical. The hospital would be enormously liable and in a lot of trouble if they had a doctor in there that didn't really do the things they claim they did. But here's an opportunity to potentially have multiple hospitals who technically are competitors with each other, but actually start to share some of the same credentialing information for doctors, so they don't need to go through the full lengthy and costly process every time. They can actually have checkpoints that they can share and get doctors practicing in their hospitals quicker. So both of these are examples of, you know, competitors actually starting to do more and more business together because they can trust the information. And the use cases obviously extend well beyond that. So where does this trust come from? These are kind of the 5 key things that blockchain brings. They don't all have to exist, but if they all don't exist, there's some trade-offs to be made. But you can get some of the benefits without these existing. You can get a lot of blockchain benefits without even using a blockchain. You know, this isn't, again, completely like new technology that didn't exist before Bitcoin. It's mostly technology we've been using a long time, just combined in some kind of new and interesting ways. But of course, we have decentralization of control, the idea that the information is immutable, that you're keeping a record of everything so that you can go back and replay that and make sure that you catch up with the current time and that everything's valid, that we have some degree of tamper resistance, that the information is validated. Importantly, there's a set of rules there, and transparency of the information. So it's pretty key. So this is, you know, it's probably a somewhat biased grid of thinking about some of these technologies, because of course Fluree sort of sits off to the right. But this is a couple dimensions, sort of one of my perspectives on the market. There's several. But when you're trying to place the vendors, because we hear so many vendors, this helps me at least understand where they tend to focus. So on one axis here, I have data flexibility. So in this corner would be things that have no data flexibility, very fixed type of information that we're tracking and dealing with. And of course, Bitcoin's, you know, a great example. There are ways of jamming like custom data into Bitcoin. There's a kind of special field called op return that you can stick about 80 bytes of information in if you want to, and if you want to pay extra for that transaction. But for the most part, Bitcoin is very single purpose. You know, it stores what it stores to do the job it needs to do. And on the left axis, we have rule flexibility, and this is, you know, smart contracts or that sort of capability. So how much can you start to change and manipulate the rules? So most of our initial blockchain use cases, of course, are financial services oriented, just makes sense. Things like currencies, digital currencies, and digital asset tracking, digital asset transfers. These are just initial, easy, hit it out of the park examples. So you tend to see them more in this single purpose, kind of not as flexible sort of system. And of course, we have things like Hyperledger Fabric, which allows you to really write a lot of your own custom code and start defining a lot of those capabilities. These tend to favor all transactional items. So I am, trading a security, I'm trading a stock, I'm exchanging money. And of course, over here, we're a little bit more towards how you'd use a normal database to track and build up schemas. So another important dimension that when you think about different blockchains and what they're bringing, beyond sort of what sort of flexibility or customization are you looking for, is going to be more on the private-public space. So consensus allows us to operate in a completely decentralized manner. Distributed is also going to use consensus. We've been using distributed for a long time. And this is mostly going to change, although it doesn't have to, but it's mostly going to change. Kind of the two spectrums are just going to be public and private networks. So private networks, the huge advantage here is that you know the participants on the network. And so all this requires consensus. Obviously, the easiest way to get consensus is you collect votes. Majority should win, unless it's a presidential election. And then, of course, majority doesn't always win. But majority should win, and that's really what Raft and Paxos do. They're just looking for majority votes and moving the network forward. All consensus is doing in this case is just making sure everybody has the same state. Everyone has the same log entries, the same pieces of information. Otherwise, they can't work together. As you get more into the public networks, these are where things like proof of work and proof of stake are doing. Could you see proof of work in a private network? Sure. I'm not sure. Again, proof of work is going to chew up network resources, so it's probably not going to make sense, but it's a perfectly valid consensus mechanism. Proof of stake, you'll see that a little bit more going into the private side. Proof of authority is really just sort of like kind of like a username password. And of course, we talked a bit about PBFT, practical Byzantine fault tolerance. But when you hear people talk about proof of work, proof of stake, and all these sorts of consensus mechanisms in that realm, they're almost always going to be talking about public blockchains. And lots of times in the enterprise, we may or may not care or be using a public blockchain. All right, so if we're going to build an enterprise app, kind of how does blockchain technology typically fit into that, or at least what's doing it now? And of course, we all need to have an agreement of what an enterprise app is. And I think in the simplest view, hopefully I don't get too many contentions on this, this is what an enterprise app is. We're, typical three-tier app. We got our client tier, we got some sort of application server tier, and we've got a data tier. And generally, we're connecting through, at the app tier, some sort of integration that's firing off, again, typically a very transactional item to the blockchain network. Does the blockchain network completely replace an enterprise app? I can't think that of any examples where that's the case. Usually, we're using this to extend the capability that we're already doing. And we'll talk a little bit, again, about this data problem we have with it. But there's a lot of information around that application that we can't fully have on the blockchain network. So typically, we're issuing transactions over. We may be trying to secure part of the information about the transaction and make sure it has, hopefully, as much integrity. That's our goal, to have as much integrity around the data that surrounds the transaction as the transaction itself. Blockchains are really, really good at proving that person or entity A, bought something from person or entity B for, say, $100 or 100 tokens. And maybe they've even done this 50 times in a day. But they're really, really bad at telling you what that was for. So we can prove that the money went across or the transaction happened, but, where's the rest of it? And that ends up presenting probably the biggest problem for typical enterprise applications. So usually, say you were going to use Ethereum. And on the public network, and you're issuing some sort of transaction or some sort of information that you're trying to store over here, what you would end up doing is you'll end up running a local Ethereum node, and then, depending on what you're using in your app tier, if you're using like Node.js, you'll use a client library that will, if I need to look up data or information that's existing in the network, it'll actually issue that request to your local Ethereum node that you're running, which is staying synchronized with the network. So of course you need to make sure this part of it, whatever you're using to help manage how that data gets over to your app, that it's up and it's running, and that it's healthy and doing a good job. But Yeah, that's about it. So how do we store information? I'll get into kind of some of the challenges we have in dealing with the information around the transaction. So this is a very, very simple solidity contract. So if you were using Ethereum, I'm not proposing you use Ethereum in any way, but it's a basic contract that in this case is storing an unsigned integer, and basically it's just setting up a getter and setter. An important consideration to think about if you're building an enterprise application is, what if I have a new field of data or a new piece of information that I need to store? Because apps change and evolve. Our requirements change and evolve. How do we handle that? And the answer becomes a little bit tough, especially in a public network, because once this is actually set up, you can't really modify it. Otherwise, it wouldn't be immutable. The people, one of the guarantees that we want to give people in a fully decentralized network is that this business logic that perhaps they put their money into for some reason, that someone can't come along and change it. So if we let people just upgrade this, then we couldn't provide that sort of guarantee. So we can't really let them upgrade it. So how do we get around that? Well, sort of the, I guess, naive approach would be you create a new contract, and now you need to transfer all the assets and information from the old contract over to the new contract. And depending on how much you have in that, this could end up costing tens of thousands of dollars to do. I've heard examples of that happening. The more logical approach is that you try and actually separate your data management from more the business logic and hope you don't need to evolve the data management piece very much. And what you end up doing is just basically having the components in a smart contract that store and manage information. And then that contract gives the contract that has your application logic in it permission to utilize it and call its methods. And that way, if you upgrade your app, you can just kind of create a new business logic tier, and all you need to do is take your contract that's storing your data and essentially give permission to the new tier. Now, of course, all your users and everyone would have to start using the new application, because the old application, you wouldn't want anyone using that anymore. So there's some challenges that you really need to think about if you want flexibility in upgrading your app. But yeah, just a simple getter and setter sort of method. If you were using Fluree DB, we set things up more like a database. This is just a simple JSON request to the network, but in this case, we're setting up a string attribute, which is a username, and we're saying it's a unique attribute, or basically a primary key. But this would be the equivalent of setting up information in that blockchain network that you're going to be storing. In this case, we're saying we're going to start storing usernames, and here's a basic schema for it. In this case, this is just an unsigned integer. I didn't give it a name, but Solidity contract, essentially doing the same thing. We're going to store this particular piece of value on the blockchain network. So the data issue that we start running into is that, like I mentioned, most blockchain transactions, they are really good at doing this. They're really good at tracking an entity, and that some sort of asset transfer, some sort of application happened. Perhaps there's a smart contract in there that's doing logic. The typical smart contract example is like an escrow. It locks up my money for 30 days, and if some event happened, then it transfers it to the other party. If that event doesn't happen, the money comes back to me. But however, regardless, during that time frame, the money's locked up. So a smart contract might make a bit more intelligence around this. But when we build enterprise applications, there is so much more information we're typically dealing with. Maybe we're conducting stuff around a particular invoice, and that invoice has products, and those products have warranties. There might be pictures. There might have been approval processes. All these sorts of items we're having to deal with in an enterprise application. We need to put that data somewhere. And if that data is completely disconnected from the transaction itself, the fact that I can prove the transaction might not be that much benefit to me at the end of the day, because if I can't prove what it was for, then it might be for moot. So the obvious thing would be, let's just store it on chain. Now, most of those, I had that chart up initially for a reason. Most of the blockchains focus on facilitating transactions. They don't focus on storing data. So it's not really a knock against them, but I will ask this. Anyone want to guess what it would cost to put a gigabyte of data on the Ethereum blockchain? Millions of dollars. So, at one point late last year, this was about $10 million to put it on there. So if you could put data on the blockchain, or if you have just a tiny bit of information, it can actually work. But at the point that you're dealing with an enterprise app that actually has a lot of information, enterprise apps typically have somewhat low transactional velocity, not that many transactions per second, but they're typically very, very rich in information and data. So it makes this a problem. So there's kind of three main solutions, and I'll talk about the pros and cons of each of these that are out there today. So the first, which I mentioned, is just store the data on chain. So the great advantage here is that there's no integration. The information about the transaction is right with the transaction itself. And this works, again, really good if you're Bitcoin, because you're not really storing much about the transaction. You don't really care about it. So where this is going to be very useful is if it's a very transaction-oriented, you just have a tiny bit of data. Obviously, the disadvantage is that, especially if you're using a public blockchain network, the cost of doing this, or even some of the private blockchain networks, the cost of doing this is still high, because they're just not designed to facilitate a lot of information like that. They're designed to handle consensus generally around transactions. This is what I hear most often being recommended, is just use a regular database and put the information in there, and then hash the data from the database, and then store the hash with the transaction. So you're just storing a little bit of data with the transaction and the hash. I don't particularly like this idea. I think most of the people who recommend doing this are people who haven't done it themselves. One advantage, of course, you have with this is that, in theory, you have unlimited data storage, because storage is really cheap nowadays. The disadvantage, of course, is now our data is separated, and we have integration that's required to bring this transaction together, which, again, not that big of a deal. These other parts start to become bigger deals to me. I need to be able to reproduce all the information, because all we're storing is a hash. And if I can't reproduce that information identically, then the hash is going to be different, even if it's one character, even if it's a sorting issue. Even if it's a character encoding issue. If I encoded it in UTF-8, I'm going to get a different hash than if I encode, even though the data is identical, in UTF-16. They're just going to look different. And I won't know what's different about them. So my concern about this is that there are a good number of failure points. And I don't know that I want to be the person that gets the call 5 years down the road when there's an issue with some sort of transaction, and it's on me to reproduce this particular piece of data in the identical way and come up with that hash so I can somehow prove it. This also tends to have one other issue, which is the data around the transactions. Even though I'm hashing all that up together, it's essentially stored like a document database. I mean, that's all you're doing with it. So any relationships in there do not have the same level of integrity. So if it's an invoice I'm generating, and that invoice is being shared on a supply chain network with different companies, that invoice may reference product numbers or product information. Well, that product information isn't being held or secured in the same way. So someone could still manipulate all the dependent data, but it still looks like my transaction is fine because I can reproduce that original invoice. So this doesn't really build on the history of information there and maintain the integrity of the historical information, but it can secure a little bit of metadata around something. Again, my big concern with this ends up being reproducibility. Not that I don't trust me to be able to reproduce it, but how many people know that the person who built this in their company is going to be there in 5 years and left good documentation, and that someone else is going to be able to have that. So I think it opens up a lot of failure points. I really love IPFS. So you don't hear this. I would much rather do this over storing it in a traditional database. it still has almost all the same challenges we talked about, except it's going to take off your hands creating that hash because it's standardized. And every tool you end up using will end up having that. And it's being stored in a technology that isn't designed to make it super easy to overwrite information, right? Databases just make it immensely easy, whether you intended to or not, to update records and destroy old information. And you may even not know that you destroyed information that was important. You just don't know. So using IPFS, you can take your data, you can encode it using any way you want. You can just use JSON encoding, encode everything in a map as a string. And stored in IPFS, IPFS will generate that hash. It's a content addressable sort of content addressable piece of technology where that hash will always be identical for that particular piece of information. You still need to run an IPFS repository locally because IPFS doesn't it's not like you're shipping it off to someone else's cloud or they're going to guarantee that they're going to be storing that for you. Technologies like Filecoin, eventually will look to try to solve this problem where you don't necessarily have to run your own node. You can pay other people to store data for you on an ongoing basis. So it's a better solution. It still has that data dependency and integrity issue where the metadata you're storing for that transaction is isolated. So if there's any references to other pieces of information, et cetera, that need its integrity, you might not have the integrity of the sub-information. IPFS is a lot like object storage. It really is object storage. So in particular, if you have things that need object storage, images, videos, things like that, IPFS is a great solution. I'll talk about how we see making this data and information available. So Fluree's approach has been to secure the information at the database source. So use it like you use a normal database. That way, all the dependent information is tracked for you. You have consistent hash replication. You actually have something you can query and do some interesting things with. So that would change the picture a little bit from this, which will still be what you want to do if you're using a public network or a very transactional-oriented network, which, again, a lot of our initial use cases are, but more to something like this, where essentially you're just using a database, and parts of the data in your database have consensus needs around it. So there will be participants that end up validating certain types of transactions. Other types of transactions, maybe you don't want on the network. Maybe you don't want validated. But if we can start to access that information in the same way we're used to in our typical 3-tier app, as far as we're concerned, we're just using another database. We don't necessarily have to deal with all those integration points. I'll talk a little bit about, and then we got at least a few minutes, I think, for questions. A little bit as far as where we see some of this information and how we make it accessible. So we've got some of these challenges we've talked about. We're creating smart contracts. We're putting these on networks. We're creating hashes of all this data. And when we're building an enterprise application, some business user somewhere needs to pull up a page. They need to check on the status of an invoice, or they need to see some sort of chart on the history of kind of where things have done. And we are huge, huge fans of the ideas of the semantic web. I even heard that kind of brought up before. But in particular, using the RDF format of storing data. And I think that we're going to see a real resurgence around this type of technology because it just starts to make a lot of sense in this context. So this is an example where we had like a database update. It ended up producing data that ended up making itself into a block on some blockchain. But if we can actually represent that data as an RDF sort of triple store, or in our case, we use sort of an extended version because we're dealing with time. We're dealing with changes over time. Then all of a sudden, we can use some of these standardized query technologies that are really amazing technologies, like Sparkle. I don't know how many people have used or played with it, but this is really, really cool stuff that hasn't totally found its niche yet, I think, to take off. And I think this is the space that really helps it take off. So what do we expect is going to change as a result of all this? Well, I think using things like RDF, triple stores, and information combined with blockchain technology to be able to guarantee the integrity. So blockchain is going to guarantee who submitted that data, when it was submitted, and that it hasn't been tampered with. That we'll end up in a world before we know it where everyone not only has a public website, every company, but also a public data store of information. Maybe it's your product catalog. Whatever it happens to be, that other third parties can interact with you. And in the same way that lots of times we download a piece of software right now and we have a SHA-256 hash that guarantees that that software hasn't been tampered with before we run it, we should have that level of integrity of all the information that comes from an organization. And I think we'll have that soon. So I think companies will end up publishing out data sets that are verifiable came from them, including history, how it's been updated and changed. So we're real big fans of RDF. I think the entire audit industry really needs to shift, or at least the parts of the audit industry that deal with verifying data. Because again, if we can trust the integrity of the information at the source, we no longer need third parties to come in and give their stamp of approval for that. What was that? Amen. Okay. So I think all public records, I think this should be the next thing that we all do is just get all of our public records onto blockchains. It's a perfect use case. It makes a lot of sense. And this one, I really believe we're going to end up seeing it. I think every database should be a blockchain database. Because why wouldn't we want this level of information security and integrity around every piece of information we have? Like, why wouldn't we? Probably the big reason we wouldn't want to is because if there's a cost associated with a time or performance. But those barriers are quickly breaking down. And if you hear things about 7 transactions per second on Bitcoin, also keep in mind, hopefully, like we talked about, part of it's because it's using a proof of work protocol. So that wouldn't be the case for a typical enterprise app. It doesn't have those same level of restrictions. We can do things really quickly. So with that, I'll conclude, and we got a couple minutes for questions if anyone has any. Yes, sir. I'll repeat it. Yeah, I think it's a great question, and one I hear a lot. And the question was, why can't 3 companies, or however many, just share a database to store information? And the answer is I think they could, but blockchain inherently is going to provide you several aspects that those databases don't automatically do. You could write code that starts to provide those same aspects if you want, but then you're starting to write code, which is fine. So the things that they're not going to, standard database isn't going to do is, for one, it's not decentralized in any way, meaning that somebody has to run that. And all the other parties have to trust that party that's running it. And we actually see this in business quite a bit, but usually in business when this happens, because they do need a master data source, the other companies will end up as part of the contract or whatever it happens to be as some sort of right to come in and audit that information because they don't necessarily know. I mean, it could be someone in their IT department. We're doing this even in the software as a service space, but a good software as a service vendor needs to have SOC 2 compliance, basically strict controls around who has access to what data because they control it. Nobody else does. So that's definitely one thing that you're going to get with blockchain technology out of the box. You can't do that with a normal database. You're also going to get immutability and tamper resistance. So the other piece is, what if someone modified a historical record? You have no real good way of proving that. Now, we can export out logs from our database and hash them and store them and things like that. So all that is possible. And again, a lot of blockchain technology they're these simple tools that we've been using for a long time. They're just combined in a way that actually makes some really neat things start to happen. So that would be at least another piece that you wouldn't have. So I don't think you can achieve the same sort of things. You'd be writing a lot of code, and some of them you can't achieve at all, but it would depend on your use case. Yes, sir.
Can you tell me the math behind what takes most 1 gig of data from the public cloud to $1 million? Why is it so costly?
The question is, why is it so costly to store information on like a public blockchain? Well, I talked about Ethereum specifically, so I'll answer specific to Ethereum. So Ethereum has 2 tokens. Anyone who hasn't really used it might not know that, but one of the tokens is called gas, and the other is ether, which is what people trade. And every time you do a transaction on Ethereum, gas is supposed to actually represent the compute power, what it ends up really costing the company. And you submit, when you do a transaction, you submit an exchange rate between the two. In the initial purpose, which I think it's a great purpose, it just hasn't worked incredibly well, but I haven't seen anything else work better, is that if Ethereum spikes and doubles in cost, well, the cost of doing transactions on the network shouldn't double as well, because it's not like my computer got twice as expensive overnight, just because the ether, doubled. So by having this exchange rate, they're trying to fix the cost of gas to a particular type of compute and resource. So storing information on Ethereum has a very specific gas price. So there's a very specific cost that it has. And that cost, at least currently, is fixed, what they end up charging for that. So the reason it costs so much is because it costs a lot in gas to store that. Why does it cost a lot in gas? The big concern with a lot of the full public networks is going to be the block size. Because you're having to deal with moving that much information, it becomes very difficult to have the network run quickly. One of Ethereum's big focuses was quick transaction times. So they do a block about every 15 seconds. Well, what if it takes more than 15 seconds to transmit the amount of data in a block? I think the average household, at least in developed countries now, has about 23 megabit per second sort of bandwidth. So that roughly 3 megabytes a second is what you could push through that, assuming you had all of that. So if you had a block that's 3 megabytes, in an ideal scenario where that was your only bandwidth constraint and it was just 2 computers talking to each other, that's going to take you a second just to move that data across. And then it still needs to be verified, and then a confirmation needs to be sent back, et cetera. So they want to make, in that case, the storage not be cheap. Otherwise, the block sizes would be pretty enormous. Ethereum's already got a pretty substantial amount of data that you have to sync up at this point. But that's the, it was focused around settling transactions quickly and efficiently, not around storing data. That wasn't their primary design goal initially. Yes, sir.
So you have a future slide up. What I just heard, I think if I were to interpret it in a future look, that very expensive future should go away.
Yeah, I think the biggest thing, the question is, in the future, does the expense of all this go away? And I think it does. Ethereum's working very hard on sharding. Sharding's, should help drive the prices quite a bit down. The thing that becomes very difficult with sharding is, of course, when you have to do transactions across shard. So there's still obviously going to be a penalty there. When we talk about an enterprise blockchain use case, if we're looking to support someone paying for my product in Bitcoin, then I need to use Bitcoin. But a lot of the things that we're looking at for enterprise blockchains, the data is already sharded. It's already a pretty small set of data that we're looking to do. So storing a gigabyte of data on an enterprise blockchain shouldn't be an issue. The problem is Ethereum's a full public blockchain, and if everyone's storing a gigabyte, then I have every company in the world maybe trying to store a gigabyte on there. But in a more of a private blockchain network, these are generally we're working with bandwidth far greater than 23 megabits per second. So the data, we have a lot more liberty on the data size in a typical private blockchain network. Again, someone may want to use Ethereum for some reason in an enterprise blockchain, and that's perfectly fine to do, but you're going to have some of those data limitations just because of the nature of what it is. And I think, if anything, and hopefully I started out with a lot of this, that's the takeaway, is that this is a big space. There's a lot of products. They do things in very, very different ways. And some of them are going to work really well for certain things you're trying to accomplish and really bad for other things. So you need to try and pick the right products that align with what you're trying to accomplish. And a lot of these problems that we hear about completely evaporate because they're irrelevant for what you're trying to do. And the product you're using, they're irrelevant for. Yes? Yeah, the question is, how does AI come into this? There's actually some projects that, boy, I can't think of the name. I know a guy who's working on something that's trying to have a lot of information available with the purpose of machine learning and AI and have it out on a blockchain standpoint. I can give you my perspective from Fluree. Our database, our query engine, is a full sort of semantic graph query engine. And part of the purpose is because we just think graph databases are an ideal format for today's modern apps. And also the reason is that is a very ideal format to feed into machine learning and AI sort of mechanisms. The other thing we do, because we're carrying around the full history of the blockchain itself, which in our case is basically database updates, we've built in time travel, so allow you to actually query any point in the database instantly without having to, restore a backup or something. Every version is available to you instantly, super speed queries to do that. But that historical context is the other component that most AI and machine learning need. They need the history. They need to look at the patterns over time. And of course, the typical database is an update and place database, so it doesn't have that. So I think part of it depends on how you structure the data to make it friendly in that manner. Certainly the historical context very well aligns with, I think, artificial intelligence and where it's going. And my guess is yeah, we're up for time. So thank you. I'll be around if anyone has any other questions.